In this video, let's try some practice problems dealing with some Algebra 2 concepts to get ready for the SAT or ACT together. Real quick before we get started, if you'd like to download a free copy of this blank PDF or to download the annotated answer key PDF, you can find a link to that below. As always, I encourage you to pause the video whenever you need to think a little bit, and I also encourage you to grab some paper and something to write with so we can go ahead and do some math together. Alright, so in number 1 it says, when simplified, the trigonometric expression of tan squared of theta minus secant squared of theta minus 1 will be equal to one of these answer choices below. This specific problem is testing our understanding of some trig identities. The only Pythagorean trig identity that you need to memorize is going to be sine squared of theta plus cosine squared of theta, which is equal to 1. And if you happen to forget this trig identity, let me show you where it is derived from real quick. If you look at a coordinate plane, and you look at the unit circle, if you go ahead and draw one line segment going from here to a point on the circle, you can see that the radius here is equal to 1. If you go ahead and draw a line straight down, this would be the y value, which is the vertical distance. If you draw a horizontal distance here, that would be x. Now remember that this would be a right triangle, so you could use Pythagorean theorem here and set up the equation that x squared plus y squared is equal to 1. Now, something to review is that when you take sine of theta on the unit circle, that's really just going to be the y value or the y coordinate, and as well as cosine of theta is just going to be the x coordinate along the unit circle. And so if you go ahead and substitute in this x here for cosine of theta, and you substitute in y for sine of theta, we can sub in and write that cosine of theta squared plus sine of theta squared is equal to 1. And then just simplifying this and rewriting it the way you typically see it, we can write cosine squared of theta plus sine squared of theta is equal to 1. And so that's how you derive this Pythagorean identity, and this is the only one you really need to know. Now, if you're wondering what this particular Pythagorean identity has to do with this particular problem where we have tangent squared of theta and secant squared of theta, let me show you how to derive the other two if you have this one right over here. So if we go ahead and take this Pythagorean identity that we should have memorized or we can derive, and you go ahead and divide everything by this cosine squared of theta, you're going to find that cosine squared of theta divided by cosine squared of theta is just going to be 1. Then if you take this sine squared of theta divided by cosine squared of theta, remember that sine over cosine is equal to tangent, so sine squared of theta over cosine squared of theta is going to be equal to tangent squared of theta. Let's go ahead and substitute that in right over here. And then finally, if we take this 1 and divide it by cosine squared of theta, remember that 1 over cosine is the same thing as secant, so 1 over cosine squared of theta is going to be secant squared of theta. And so in the future, if you just have this one Pythagorean trig identity memorized, if you divide all the terms by cosine squared of theta, you'll derive another one of those Pythagorean identities. Similarly, while we don't need it for this particular problem, if you divide this original Pythagorean trig identity by sine squared of theta, look what we're going to get here. We're going to get the third one. So if we take this cosine squared of theta and divide it by sine squared of theta, remember that cosine over sine is just going to be cotangent. So cosine squared of theta over sine squared of theta is going to end up being cotangent squared of theta. Then if we go ahead and take this sine squared of theta divided by sine squared of theta, that's going to equal 1. So we're going to go ahead and add 1 here. And then finally, if we have 1 divided by sine squared of theta, recall that 1 over sine is the same thing as cosecant, so 1 over sine squared of theta is going to be equal to cosecant squared of theta. So again, if you just have this first one memorized, you can go ahead and derive the other two Pythagorean trig identities as needed. Now notice in this particular expression, we have tangent squared of theta minus secant squared of theta, so let's go ahead and rearrange this Pythagorean identity over here. Now if we go ahead and rewrite this Pythagorean identity and we can go ahead and subtract secant squared of theta from both sides and subtract 1 from both sides, we should be able to rewrite this and say that tangent squared of theta minus this secant squared of theta, and that's going to be equal to negative 1. So if we know this expression over here is equal to negative 1, then we should be able to take this expression right over here and substitute in negative 1. And if we do that, we're going to end up saying that we have negative 1 minus 1, which is equal to negative 2. A would be our answer choice for number 1. So while that was definitely maybe a little bit more information than you might have been looking for this number 1, hopefully that helps you out with some future problems as well. Alright, here is number 2. Looks like we're going to be dealing with some logs here. In this problem, if log base a of x is equal to p, and log base a of y is equal to q, and also we see that log base a of z is equal to t, we're supposed to figure out what log base a is of this quotient here of x squared y cubed over this square root of z. Now essentially they're just asking to see if we can take this condensed version of this logarithm and expand it. And the reason why we can tell that is because if you look at each of these answer choices, all these are in expanded form where we have some addition signs and subtraction signs. So keep in mind that when you're trying to expand logarithms, we're going to turn our multiplication and division into addition or subtraction. And on the flip side, if we were taking these expanded versions and we wanted to condense these, we would go ahead and turn the addition and subtraction into multiplication and division. Similarly with exponents, we'll talk about that in just a moment, but those exponents will go ahead and become coefficients or multiply by the logarithm instead, or vice versa. All right, so starting off here, let's go ahead and just rewrite this logarithm. Next, what I'm going to do is do two steps in one. First of all, I'm going to take this square root of z and rewrite this from radical form into exponential form. And I'm also going to go ahead and separate the numerator and denominator. And remember that this division sign, if we expand it, it's going to turn into subtraction sign. So what we're going to do here is we're going to write log base a of the numerator, which is going to be essentially this x squared y cubed. I'm just going to put this in parentheses so you know it's this entire thing. And then we're going to be subtracting, because when we expand logarithms with division, if they have the same base, we can rewrite this as subtracting two logarithms. This is going to be log base a. And instead of writing the square root of z, I'm going to go ahead and write that this is going to be z raised to the 1/2 power. That's just going to be that radical form written in exponential form. So if we go ahead and expand that multiplication, we can go ahead and write log base a of this x to the 2nd power. And then that multiplication becomes addition because they have the same base of a. So we have plus log base a of y to the 3rd power. And then we have minus this log base a of the z raised to the 1/2 power. All right, the last thing we want to remember about logarithms is one of these properties with their exponents. So in the condensed form, we have exponents, but if you're going to turn it into expanded form, all these exponents can go ahead and multiply by the logarithm itself. So if we're going to go ahead and expand this in exponential form, it's condensed, but if we move that in front, we're going to have 2 times log base a of x, that is when it is expanded, plus 3 times log base a of y, and then minus 1/2 multiplied by log base a of z. In terms of what we needed to know about logarithms for this problem, we are all done. The rest of this is all about substitution here. So now what are we going to do? Well, if we take a look at this log base a of x, recall that this log base a of x is equal to p, so we're going to go ahead and make a substitution there. Then if we take a look at this log base a of y, we can see that log base a of y is the same thing as q, so we're going to make another substitution there. And then finally, if we take a look at this log base a of z, we can see that log base a of z is equal to t. So this last step, we're just going to be making some substitutions. So let's go ahead and swap out this log base a of x and replace it with p, swap out this log base a of y, replace it with q, and swap out this log base a of z and replace it with t. Putting this all together, we're just going to have this 2 multiplied by the p, plus 3 multiplied by the q, and then we're going to subtract 1/2 of this t. Looking at this final expression, we can see that d would be our answer. All right, here is number 3. For number 3, we can see that for all the values of theta for which sine of theta and cosine of theta are positive, we need to figure out what this expression of this square root of 1 minus cosine squared of theta all over sine squared of theta times cosine of theta is equal to. So similar to number 1, we should be thinking of trig identities here as well. Now notice that we do have a 1 and we have these sine squared and cosine squared, so I'm thinking of these Pythagorean trig identities as well again. So I'm just going to go ahead and write down from the beginning that we have the original one of sine squared of theta plus cosine squared of theta is equal to 1. Remember, that's the only one you really need to memorize. Now, if you go ahead and rearrange this equation here, if you go ahead and subtract cosine squared of theta from both sides, we can see that sine squared of theta is the same value as 1 minus cosine squared of theta. Now, the reason why I did that was because if you take a look at this 1 minus cosine squared of theta, we can see that that exact expression is in the numerator of the expression in the problem. So let's go ahead and swap out the 1 minus cosine squared of theta for this sine squared of theta. So substituting in the sine squared of theta for 1 minus cosine squared of theta, we're going to go ahead and put in the numerator under this radical, the square root of sine squared theta, making that substitution. That's going to be all over sine squared of theta. We're going to multiply this by cosine of theta. Now remember that the sine squared of theta here is really just sine of theta multiplied by sine of theta. Sometimes it's a little confusing where that little 2 is written, but if you take the square root of sine squared of theta, that's just going to equal sine of theta. So simplifying this a bit, we're going to get just sine of theta in the numerator over the sine squared of theta in the denominator, multiplying this by cosine of theta. Now, if you want to expand this a little bit on the denominator so it's a little bit more clear, we can write sine of theta for the numerator, and on the bottom, if you want to write sine of theta multiplied by sine of theta, that's also okay. We're going to multiply this by cosine of theta after. But if you like writing it this way, just so you can see it, we can cancel out one of the sine of thetas with one of the sine of thetas on the bottom, or you could have done that without writing this as well, and that's fine. And so if you do that, notice that we only have this cosine of theta on top, and then we have this sine of theta on bottom. Now, another one of our trig identities is that if you know that sine over cosine is equal to tangent, then cosine over sine, or the reciprocal, is going to be equal to cotangent, which is the reciprocal of tangent of theta. And so using some of our trig identities, we can see that C would be our final answer. All right, here is one final example. For number 4, it looks like we're dealing with some exponents. The question for number 4 is which of the following expressions is going to be equivalent to this expression here. In the numerator, we have 3 multiplied by 3 raised to the 2x minus 5 power, all over 3 raised to the x plus 1 power. So when you're studying for the ACT or SAT, obviously there are so many rules and concepts you need to memorize. So again, whenever you have these types of problems, a good test-taking strategy for when they ask you which one of these expressions is equivalent to this expression, if you don't remember all your strategies, you can just let the variable equal some value. Again, stay away from 0 or 1. But if you do that, you can go ahead and just plug in values and see what we get. So let's go ahead and say let's let x equals 2, see what the value of this expression would be equal to when x is 2, and then let's go ahead and just plug in 2 for each of these as well. So we can go ahead and see what's going to happen here. Now, if you plug in 2 into this original expression, then we're going to have this 3 multiplied by 3 raised to the 2 times 2 minus 5 power. Well, 2 times 2 is going to be 4, and then 4 minus 5 is going to be negative 1. So in terms of the numerator, we're going to have 3 multiplied by 3 raised to the negative 1 power. And then in the denominator, we're going to have 3 raised to the 2 plus 1 power. 2 plus 1 is going to be 3, so that's going to be 3 to the 3 power, or 3 to the third power. And so hopefully this looks a little bit less intimidating because we don't have variables. You still kind of need to know some of your exponent rules, but maybe this is a little bit simpler to look at. If you multiply 3 to the first times 3 to the negative first, keep in mind that you're going to go ahead and add those exponents together. So it's going to be 3 to the 1 plus negative 1. That's that shortcut using that product property. And then on the bottom, we still have 3 to the third power. And underneath here, we're going to say, well, this is going to be really just 3 to the 0th power over 3 to the third power. You still need to know 3 to the 0th power is equal to 1. And on the bottom here, we're going to have 3 to the third power, right? So this would be it in simplest form if x was equal to 2. So I guess if you take a look at A, if x was equal to 2, would that equal the same thing? Well, I think this would be equal to 3 to the 9th power, which is definitely not the same thing as what we have over here. So I'm going to go ahead and just cross out A. If we go ahead and look at B here, if we plug in 2, that would be 3 raised to the 2 minus 5 power, or negative third power. 3 to the negative third power is actually the same thing as this. Keep in mind that if you move this exponent up, or the whole power on the bottom to the numerator, it would be 3 to the negative third power. And so again, hypothetically, if x was equal to 2, we would find out pretty quickly that B would be our answer choice, or be the most simplified version of this one over here. Just because if you plug in 2 here, you would get 3 to the negative third power, which is the same thing as 1 over 3 to the positive 3 power. Now, well, that's again a strategy you can use by just plugging in a number just to get rid of the variables. What we can do is go ahead and now solve this the actual way with using our properties of exponents. So let's go ahead and rewrite the original expression here. It would be 3 multiplied by 3 to the 2x minus 5 power. And that's going to be the whole thing on top of 3 raised to this x plus 1 power. All right, so it's not terribly more work if you already just understood those properties we just talked about of the exponents, but the key thing here is putting a 1 at the exponent for this first 3 that you have here. And keep in mind, if you're going to multiply this 3 to the first power by 3 to the 2x minus 5 power, again, we're going to use that property where if you're multiplying 2 powers with the same base, you can go ahead and add those 2 powers together, exponents together. So we would rewrite this as 3 raised to the first power plus this 2x minus 5. So again, we're really just adding these 2 exponents together, and that's all going to be on top of this 3 to the x plus 1 power. Now, if you go ahead and combine some like terms in the exponent of the numerator, we're going to get 3 to the 2x and then minus 4 power. and that's going to be all on top of this 3 to the x plus 1 power. And then we're going to use our quotient property here, which lets us know that if we have the same base of 3 and 3 here, what we can do to simplify this expression is just subtract their exponents. So if we go ahead and subtract these exponents, we're going to say this is going to be 3 raised to the, and it's going to be 2x minus 4, subtracting this x plus 1. Make sure you put that x plus 1 in parentheses because we're subtracting the whole thing. Now if we go ahead and just clean this up a little bit, we're going to have to distribute this minus sign to both of those terms there. But we're going to have, let's move down and give a little space here. This is going to be 3 raised to the 2x minus 4 minus x minus 1 power. And if we go ahead and combine some like terms, 2x minus x is just going to be 1x. So that's going to be 3 to the x power. And then we're going to have this negative 4 minus 1, which is going to be negative 5. So it's going to be just minus this 5 here. And so if you take a look at this expression here that we got, leaving the x in there the entire time, you can see that does match up nicely with what we had for our answer choice B. All right, so there you have 4 different practice problems covering some concepts from Algebra 2 that you might have needed to brush up on a little bit just to get ready for the ACT or SAT. If you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing.